All right, gang, Math 6620, more on logistic regression. And I may be playing it over safe on posting this video, but I had a situation with a doctoral student one time that scarred me for life. It scarred her even more so. What happened with her is, I demonstrated many times how to run a logistic regression model. And we dove into things like model diagnostics and assumptions and choosing the best model selection, if you will. And I forgot, I guess, to cover some basic ideas with her. Number one, how to identify what's actually being predicted. Now, if you think about it, over to the right screen, back in the linear regression, simple linear regression world, if we had a quantitative predictor, there was a natural ordering. The dependent variable had to be quantitative, or we wouldn't be using simple linear regression techniques. So there was a natural ordering uh, because of the quantitative nature. So if you wanted to examine the difference or the relationship between high school GPA and first year college GPA, more specifically, if we wanted to predict first year college GPA from high school GPA, the interpretation of the coefficients very simple, straightforward. As our X, in this case high school GPA, increases 1 unit, then the predicted Y, in this case the first year college GPA, increases or decreases based on the coefficient in our model, which would be our slope. We don't have those conveniences in logistic regression. As my doctoral student found out, she didn't fully understand the way that her dichotomous variable was being coded, and she interpreted her coefficients and the odds ratios exactly reversed what she should have been. It was a horrible situation because she defended. We figured out very quickly that she had these things reversed. She had written her chapter 5 to support the results from chapter 4, which were uh, reversed, and she completed her PhD, but it was a messy process. So again, maybe I'm playing it too safe here, but I would much rather post a video if it's not needed than to not post one and get in a situation like that. So for logistic regression, we have to realize that our Y variable is dichotomous and there's no natural ordering. Now, sometimes there may be an ordering that we think is natural, maybe success versus non-success. Yes, you might say, well, the success is better than non-success. Not necessarily. Maybe the purpose of the study is to examine characteristics and sets of characteristics which lead to not succeeding in a program. And maybe even that we have a set of diagnostics that lead up to, we're trying to predict whether a student chooses a red horse or a blue horse as their favorite in the end of some some set of manipulative um, factors. But so anyway, we have to proceed with the understanding that our dependent variables dichotomous, and there's not a natural ordering. So the previous video, I said when we interpret the coefficients, we do so with respect to our set level of the predictor and a set level of the response variable, our dependent variable. And I think the example I used before was gender predicting anxiety. Now, I could set this up any way I wanted. I could predict the odds of a female having low anxiety, male having high anxiety. But the point I'm trying to make is we have to establish this in order to be able to appropriately interpret our coefficients. Now, what I did to force the issue, if you will, is I added uh, two variables, A and X and GEN. And what I did is I forced the issue that gender equal 1 is male and anxiety 1 is equal to high. So I've set the criteria for my test. And when I do that, you can come down and see just using zeros and ones that I have 12 0 zeros, 39 ones, and so on and so forth. Now, what I can do, again, because I've established that I'm making these odds calculations based on y equal 1 and x equal 1, I can do the odds that y is equal to 1 given x equal 1 to the odds of y equal 1 when x is not equal to 1 or x is equal to 0. You can see that the odds for y equal 1 when x is equal to 1 would be 38 over 14. And you can see that the odds when y is equal to 1 when x is equal to 0 is 39 over 12. When I divide an odds by an odds, I get an odds ratio, which is ultimately 0.8352. Now, what I did next is I ran the model again, just using zeros and ones, because again, there's a natural ordering there, but the way that I've forced the entry of these using zeros and ones, obviously one is bigger than zero. So I ran the model, and you can see that I get the coefficients, negative 0.18 and 1.1787. I would care about this, but in this demonstration, that's not what this is all about. What this is all about is to show you how to manipulate R to get the outcome that you are seeking. Now, so I have the estimates, and the model that we have, as you can see from the output, is 1.787 minus 0.1801. Now notice that if we exponentiate the coefficient of the predictor, take e raised to that value, we get 0.8352, which by more than just convenience is what the odds ratio is that we calculated manually before. Again, for you to be able to interpret what 0.8352 means, you have to understand the structure, the framework of identifying your X label or your X comparison value and your Y comparison value. So it leads us easily to make an accurate interpretation. The odds of Y1 equal, or I'm sorry, Y equal 1 when X is equal to 1 is 0.8352 higher than the odds of Y equal 1 when X is equal to 0. I can't stress how important it is for that to be tattooed to your brain to where that becomes clear. And it's not always clear, and I'll demonstrate that in just a second. So also recall that the probability of X can be found by taking e to our b0 plus b1x over 1 plus e raised to the b0 plus b1x. So when x is equal to 0, we insert 0 in for x, so the second term disappears. So we get 0.7647, and when x is equal to 1, we put a 1 in for x, and we get e raised to the 1.1787 minus 0.1801 in both places, and we get 0.7308. Now, R has a cool feature. We can find the probabilities just using fitted. Again, I named my model, so I can take fitted model, and I can see that the first, let me expand this a little bit just temporarily. I can see that the first subject is male, and I can see that the probability of having a high anxiety is just as we reported it or calculated it at 0.7308. The second person student is female, so 0.765, which is exactly what we calculated over here. Now, here's the way I wanted to proceed next. Let's and again, I just made a few notes here. This is easy to interpret when we force the issue with zeros and ones because we kind of create a natural ordering. Ones are just bigger than zeros, and zeros serve as our reference category. But let's say we come in just cold turkey, if you will, and we want to run our model on anxiety rank and gender, which as you notice up here, anxiety rank is high and low, and gender is males and females, not a natural ordering of zeros and ones. And this is typically the way that we're going to run our logistic regression models. But we have to have a clear framework from which, by which, we can make our interpretations correctly. So, uh, so let's just say that we just kind of blindly run our model. How do we know what we're predicting and how the predictor is categorized? So that's what I did right here is I ran the model number 2 based on anxiety rank over gender. These are, again, anxiety rank highs and lows, gender ends in males and females. And I did a summary. And notice what happens. You might say, well, we get the same thing. Well, actually, we don't. The estimate for the intercept was a positive 1.1787, and the estimate for gender was negative 0.1801. If you think the positive and negatives don't matter, talk to your banker. He or she will tell you otherwise. So the coefficients are similar, but obviously different. This is because, unlike with zeros and ones, there's no natural ordering. So the solution is we have to determine what we want to predict and force how we want the problem to be set up. So I do that by setting my reference categories. And what this actually does is it sets what I want recognized as my zeros. Now, again, let me pump the brakes a little bit and tell you, if we have a quantitative predictor, we still have to worry about how the dependent variable is categorized, how it's labeled, so we can interpret correctly. But we wouldn't have to worry about the predictor being categorized or use the relevel, because again, there's a natural ordering. So this command right here is telling me that for gender, I want female coded as 0. This is telling me that I want anxiety coded, I'm sorry, anxiety of low being coded as 0. Now you can tell I got a little sloppy here because anxiety is quantitative. I needed anxiety rank or ANX rank. So I corrected that right here. Now, when I run my model, notice how I get the same estimates. So if you didn't become aware of this, if you will, and you start writing up your results, and you just kind of assume that the base is, and it makes it clear here that your code 0, that male is coded 1 and female is coded 0. This is obvious from the output. But for the dependent variable, it's not obvious which is coded 0 and which is coded 1. So we have to, again, force that. So then you can see that we get the output exactly as we did before, because we force the issue and can make a correct interpretation. Now, I ran the fitted for the model. I think I called this model 3, didn't I? And you can see that the calculations we get over here are the same. So again, extremely important. And I don't know how long this video will take, probably around 15 minutes, but I think just going through and identifying the issues that can arise if we don't state clearly, especially the dependent variable, because the independent variable is going to be somewhat known by the labeling in the coefficient table. All right, gang, that's about it. What we'll do, we'll move forward with another example. We'll get into testing assumptions, interpretation of coefficients again, and effect size, power. We'll get into more stuff on logistic regression. All right, take care.